Privet or hello. So, how's my Russian? Okay. I will continue in English from now on. Probably I don't any Russian. At least now I got my transliteration of my last name and first name into Cyrillic letters. So in case you're wondering why I sometimes stare at your badge, I try to figure out how to actually pronounce your name, because I know about now 70% of Cyrillic letters, and I try to guess your names. I would appreciate if you help me. So, SSLError, what's it all about, and what to do when it goes wrong? To start with a small story, let's imagine you're in a beautiful Russian countryside at a nice venue with a good pool. You maybe have a swim or a cocktail, you relax, and suddenly your pager goes off. There's some kind of problem in your production system. You go to your room, already annoyed, look at the logs, and it looks like that. You think, what the hell is going on? You don't understand anything. So this talks about helping you understand some of the things that can go wrong. So, hi, I'm Christian Heimes from Hamburg. I've been doing Python for several years now. I'm a co-developer for 10 years now. I'm maintaining the SSL model for a couple of years now, and I'm part of the security team at Python. During my work time, I work at Red Hat as security engineer on identity management, authentication, single sign-on solution called FreeIPA, with a CA system called DocTag, and some other security-related things. This talk will be about SSL, so quick agenda. I'll show you a bit of history, high-level view, what's SSL about. I'll talk about different kind of problems you might encounter, connection issues, bit of crypto to get you on speed, what can go with the handshake, with certificates, root CAs, hostname verification, and finally I'll summarize everything, give you some tips, resources, links, and books you can use. I will also introduce you to some tools, and since I have an hour, which is a lot of time, we'll have plenty of time for questions, and if there's no questions left, I will release you early for a lunch. Before we go into actually high level, let's do a bit of commercials. Should you actually deploy TLS? Should you use SSL? Well, the short answer is, yeah, you should. You really should do that. There are multiple reasons. I think the only argument against TLS SSL is people think it's too slow, but SSL only has one performance issue. It's not widely used enough. All the rest can be optimized away. To give you a short example from a guy called Troy Hunt from Australia, he did measurements how fast HTTP against HTTPS is. So if you download a big website of HTTP, it might look like that, takes like 5.5 seconds or so, almost 6 seconds. But if you switch to HTTPS, then you see that. Bam, ready, done. 1 or 2 seconds. Because browsers these days use HTTP2 that can use certain tricks to make connections much faster and tunnel all your traffic through one single TCP connection. And that only works over HTTPS. So if you deploy websites, use that. Also, what's going to happen like next week, you'll see that if you go to the PYCON Russia website, because PYCON Russia doesn't use HTTPS yet, and Chrome will show you a very nasty, not secure box, starting, I think, next week. That's Chrome Better. I downloaded yesterday and make the screenshot. So, solution for you, especially if you don't have don't want to invest any money into certificates, use Let's Encrypt. You can get a free certificate that works perfectly fine. They've even forced you to renew the certificate every couple of months, so you actually will learn how to renew certificates and not run the issue like 5 years from now, your certificate runs out and you no longer know how to actually renew your certificate. So, awesome thing. I highly recommend it. History, SSL TLS, it's a bit confusing because 1 is bigger than 3 and 1.2 is actually hex 303. Yeah, because they decided to change names like in the middle of the standard. So there's SSL, there's TLS, there's something called start TLS, which is actually TLS, but with a little twitch. But why different names? So SSL stands for Secure Sockets Layer and TLS for Transport Layer Security, which is actually two names of the same protocol family. Many years ago, Netscape, the previous company is now known as basically Mozilla, wanted to start e-commerce, so transmitting credit card information. So they came up with SSL version 1, which apparently was so bad, it had rumors that the standard was broken on paper during the initial meeting. So it was never released. 1995, they released SSL version 2, which was also so bad that a year later, they completely did a redesign, SSL version 3, which is totally different than version 2. At that time, also the standardization body IETF came into board, and they wanted to make an official standard, but they didn't want to use the term SSL from Netscape, so they decided, let's make TLS 1.0, which actually SSL version 3.1, which had only had some minor improvements, but a completely new name. TLS 1.2 came out almost 7 years later with several protection against attacks, CBC attack. They also changed how they do initialization vector. It's a bit more to crypto. I'm not going into details, but they added some small improvements. TLS 1.2, which came out 2 years later, actually had some big improvements. Official support for AES. Something called AEAD, which is a way to verify cryptographic operations and data transmitted in a better way. So if you encrypt data, it's not protected against somebody changing your data. You need to do some extra steps, but with AEAD algorithms, so for GCM, Gauss counter mode, you can do encryption and verification checksums of your encryption in one go. And hopefully soon we got TLS 1.3, which is a major improvement over TLS 1.2. They're still struggling with the standard. It's now, I think, in the final draft. Last discussion round will be finalized soon. They had several issues with hardware firewalls. They had to change the protocol again. That removes lots of old craft and only supports latest best crypto we know. So SSL is the old name. I still use SSL myself because it's OpenSSL. The standard library middle in Python is called SSL, but the standard actually these days is TLS. There's several libraries. OpenSSL, the most important one for Pythonistas. There's one from Mozilla Firefox, Apple and Microsoft, their own products. But yeah, there are also several Python models that can do SSL. So the one I maintain is the SSL model. Another one is the PyOpenSSL wrapper, which contains also SSL interfaces, now maintained by Hunek Schlabach and Alex Gaynor and Paul Kara. There's bindings for NSS, the Netscape library. Red Hat used a lot, but we now also standardize on OpenSSL. Corey Banfield from Python Request ULIP 3 wrote a wrapper for the Apple interface, secure transport, and more. And to use the Python SSL, just a quick overview. It wraps OpenSSL APIs very closely internally. You create some contact, it's just a configuration space that holds information, which protocols, which ciphers, which certificates you use. Again, I will explain the details later. You can do that manually or with a helper function, and then you open a network connection to a host and port, wrap the network connection in an SSL connection, and then you get a secure socket back. And finally, you can send or receive data. And throughout these steps, there can be multiple issues, starting with issues like the actual TCP handshake, wrapping that validation like this host name or the certificates you load here can go wrong on multiple levels. And that's to talk about. So, high-level overview. I will show you the overview about SSL and then go into specific smaller topics throughout the talk later. Since I couldn't use PYCON Russia as an example, I gave the same talk in Prague a couple of weeks ago at PyCon Czech Republic. So most people think SSL is just this tiny green lock, but it's much, much more. And it's also much more than encryption. because TLS not only encrypts traffic, it also verifies who you talk to. It protects you from other attacks like somebody recording what you do and replaying your transactions, like you will send me $100 or 100 or 1,000 rubles, and I would just record what you send to the bank and repeat it over and over again and just get lots of money from you. That's also not possible with TLS. I'll skip over the Wikipedia definition. That's for my slide I will print out. So core feature of TLS SSL is, for one, obviously the encryption, so nobody can read what you transmit over the wire. It's also something that's called protocol and application agnostic, so you can transmit lots of different protocols over TLS SSL, not only HTTP, but mail, web server communication, MySQL, Postgres, IMAP, and lots of more. There's also integrity check, so nobody can mess with what you transmit. Nobody can replay what you transmit. And you authenticate the server. It means if you talk like to your email provider, your bank, you can be very sure that you actually talk to your bank, not some attacker that is between you and the bank and intercepts the traffic and modifies the traffic or sniffs your passwords. And you can also do something called client-side authentication. It's rather an enterprise feature where you have like smart cards or special certificates on your computer that then can be used to authenticate. It's more secure than passwords, but much more complicated to set up. And it's also very extensible, which was very useful for developing TLS 1.3. Wraps lots of standards, which makes it hard to understand, and it also goes through lots of different stacks, which makes it also hard to debug. So can go wrong from starting from DNS issues to some crypto things, and X509 public key infrastructure certificates also very complicated. But let's see how much I can cram this talk. So connection issues, or what happens when you connect. So what we do when you connect to a TLS server, first we have to do some kind of agreement. What can the other side talk to me? Like which ciphers are supported, which version are supported. That's called negotiation of the parameters. Then we need to authenticate the other side. And finally, we need something to encrypt the traffic. So we have to agree on something that is called in TLS language pre-master secret. From the pre-master secret, we can derive other secrets that are then used to both protect traffic and encrypt traffic. Looks a bit like that. So you first have to look up your host, do like TCP handshake, standard network connection. You send a hello with some information. You get a hello back. If everything goes right, then you send something else, send a finish, and then you can start to do some encrypted traffic. The server also sends you some finish back with some additional fields, and at that point, you're ready to actually transmit your data. So these greenish steps are not encrypted, and at the very end, we can actually start to do encrypted things. Even the first thing, connecting to the server like DNS lookup, TCP handshake, and sending the first hello, there are multiple things that can go wrong. One, if you get something like name or service not known, usually means you have a host name that is unknown, not in DNS, or you have DNS configuration issues. Yep, sometimes it's DNS. Connection refused often means there's a firewall between you and the server, or the server is down, has crashed. Getting information like wrong version number can be multiple things. Just closing with error number 0 can mean multiple issues, and sometimes the server just doesn't respond and it's dead. It's often also firewall issues, or you have like connectivity issues with something wrong with routing or your Wi-Fi, or yeah. The first thing what I do when I run into issues is first see if the host is actually up. So do a DNS lookup, maybe ping the server, that also helps. Send a ping, you get a PONG reply back, and depending on how you do that, you might actually end up doing like IP44 and IP46. The different protocol that looks similar, but that's an example with IP44. Sometimes IP46, sorry, that's IP46. that sometimes doesn't work properly depending how, like hotel networks are prone to not work about IPv6. It's always a hassle to diagnose that, but just starting to see, is the server actually there? It helps. There are other tooling, like sniffing on the network. Tcp Dump is something if you work on a server that doesn't have any UI, it helps. In this case, I'm connecting to a local host pod, so that means I'm sending a sync request. It means I'm starting a TCP handshake. I get a reset back. That usually means, okay, there's actually no host, no service listening to that port. And it tries 2 times. First, was it hidden somewhere? So this one is over IPv4 here. And then it tries again because local host on my machine maps to both IPv4 and IPv6. That may help, but later on I'll show a better tool that makes that like better explorable and better understandable, but that's gibberish even to me. Also very useful tool, most people totally not get is using curl with -s-v. It gives you very, very lengthy output of all the steps that are happening when you connect to a server. And finally, between curl, wget, or Wireshark, we'll show later, you can use port scanning, or if you have access to a server, read firewall logs. So that will give you the first step to actually understand on a very low level, can you actually do a basic connection to a server. Or very useful, I hope the video works. Oh, it works. Is make a screencast. You can use this as a labs tool, which gives you all these checks, including many more checks. So certificate information, information which kind of protocols are negotiated, which cipher suites are supported, even which kind of operating system and version of browsers and Android and Apple phones can do which kind of connection. It's a bit hard to read. I will upload also this video when I upload my slides. Okay. Technology, fantastic. Doesn't go to the next slide. I think it doesn't like my video. Or yeah, just use your browser. So if you test a website, web service, just try to connect with your browser. Your browser gives you other good error messages. So, Ssl handshake. So once we have connected like a TCP connection, we want to upgrade that to TLS. And I'll show you a bit more now. So first we do, when you do a client hello, send hello to the server, we tell the server we support like different versions of TLS, we support certain ciphers, and we send some random information, which is useful for something I'll explain a bit in a minute. The server will reply back with the server hello, saying, oh yeah, I want to speak like TLS 1.2, and I know that cipher suite will use that, and maybe these elliptic curves, and also random value. And one of the most common issues you may have is that error, either wrong version number or no response at all. That often means that you're talking to a server that doesn't support TLS at all. May not even be like TLS port, or maybe you have error in your configuration and port 443 of Apache is not configured to serve TLS, but standard HTTP. So, but there are actually more problems that can map to either unsupported TLS or wrong protocol. So if you, the server doesn't support like the latest version of TLS, you have a very ancient machine that only supports SSL or TLS 1.0. The alert handshake failure is a very generic error that says something went wrong. Not very helpful. Alert protocol version sometimes occurs when the server doesn't know your protocol, like SSL 3.0 server, you try to talk to newer version. And very nasty one I encountered just a couple of days ago on the Python bug tracker. Somebody was complaining that the latest version of OpenSSL just gives him error number 0. It took me a while to test that. In that case, the person tried to use a newer version that only supports latest SSL versions, no longer SSL 3.0, and no longer the most modern cipher suites. And the other server, instead of sending back an error message, just decided, no, I don't want to talk to you, I don't understand you, and closed the connection without sending any kind of error indication. That might happen. And that might also happen if you get like a call the wrong function, then you have like typo in your Python program. This alert handshake failure, or TLS alert number 40, is a very generic error, and it's too bad you don't get better information back if you run that. That can often mean that the other side doesn't speak the same crypto algorithms. Happens often when you update OpenSSL to a new version that has no longer support for bad crypto, or unsupported TLS version, or some other parameters related to elliptic curves or signatures, and there's no direct way to get from that error message to the root cause. Then you have to use extra tooling, for example, a tool called SSL scan, which will basically configure the SSL context for a specific version, and just one cipher suite tries to make a connection and then sees what's going on. You see here, for example, tries SSL version 3 with that algorithm here, it rejected, and some of them succeed. So it has to create for every line a new connection and tries to make a handshake, and then sees what goes wrong. And this looks kind of a bit of gibberish, but it's not that hard to read. So small interlude, intermezzo, introduction to crypto 101 and how the cipher suites work, because you need to understand a bit of crypto to diagnose issues. So first thing we need for lots of things is something called hash functions. Hash functions will give you like a fingerprint or checksum of data. You can pass in as much data as you like, and it always gives you a fixed amount of data back, like usually a couple of bytes, which identify this data you have sent. You can't map directly back from the checksum to your data, but any kind of data gives you like a unique checksum. Also, of course, we need to encrypt. We use different kinds of encryptions. For the data itself, you use something called bulk encryption. That is very, very fast encryption that can handle lots of data. Well, the most famous one we currently use is AES. The other ones, the red ones, are old standards you should no longer use. So RC4 is broken, SSS is broken, DES has been broken for many, many years. SHA-20 is a new one. That is for just the data you send, like images, HTTP, HTML, CSS, videos, whatever. But we also need some ways to identify a peer and to agree on this pre-master secret I explained in the beginning. For that, we need to use public key crypto. It's a slightly IKEA-like explanation. Public key crypto or asymmetric crypto means we have like two parts. One part that only we know, the private key, and some part that we give to the public or to the other person or the other server. And the private key can either do something called signing, so we can like write a signature on the data, and then the other peer can use the public key to verify that only we signed that, or the other peer can use this public key to encrypt data, and only our private key can use some math tricks to decrypt that. Without the private key, it would take like millions of years to decrypt the data, or quantum computers. And the different kinds for asymmetric encryption, Al-Jamal used in GPG. There's RSA and specific modes that can encrypt data. So there's also the signature algorithms. Different variant of RSA can use signatures. There's DSS or DSA, which is an old standard. These days, we often use elliptic key crypto, so ECDSA or EDDSA, which work instead of finite math over elliptic curve math. And these are used faster and smaller keys. And the final thing we also have is something called key agreement protocols. It's a way to agree on a common secret without actually giving away the secret. Yeah, it sounds a bit fuzzy, but Wikipedia has a very good explanation with colors. We both agree on a common color, and I mix in some color I only know, and the other side mixes in a color on the other side will know. And then we exchange these mixed colors, and I add my color to the combined color I got for the other side, other way around, and that way we both have the same end color. An attacker, in theory, could just grab both of these colors too and mix these public key colors together, but the attacker would get 2 times this yellow color, and obviously the wrong result. So that's called a key agreement protocol, Diffie-Hellman. And all these building blocks I just showed you, they form this cipher suite. We have key agreement, we have authentication algorithm, we have bulk encryption, we have some kind of mode for the bulk encryption, and this one-way hash function to verify traffic. And yeah, they look like that. So we have TLS, we have elliptic key Diffie-Hellman ephemeral with elliptic query DSA, we have AES encryption in gallows counter mode, and SHA-384 to do the fingerprinting, the hashing. They'll all build their way, and once you know the trick how to get the different parts, it's actually easy to read them, except OpenSSL, because OpenSSL decided, why use standard names? We just invent our own names. Yeah, look like that. So sometimes they look similar, sometimes they just omit whole parts. So in modern Python, you can use some helpers, it's explained in documentation, to get the information from the cipher suites. And this, additionally, you're Russian, so you're a bit special, because if you do some contracting with the Russian government, you also have to take GOST into account. Because why would the Russian government ever trust American standards? You never know. Yeah. And if you deal with Chinese government, they also have their own standards, but yeah. So, TLS handshake. Let's go back to the handshake, because we only filled in the first bits. So we have seen that picture, we sent some random information, the cipher suits, got some cipher suits back, and now we have to agree on a secret. And the old way we used to do like TLS 1.0 and SSL used something called RSA key exchange, where the server sends back this hello, including the certificate chain, and the client then selects a random value, which is the pre-master secret, encrypts that with the public key of the server, and the server can use its private key to decrypt the secret, and they both have the same secret, which has one big downside. If the private key of the server is ever compromised, then an attacker with large disk space somewhere in the desert of Utah, I think, could decrypt all traffic they ever recorded over the last decades. That's why we no longer do that way. Instead, we use the new way, Diffie-Hellman. So instead of having the client pick the secret, the server picks like a group, that's the base color, and some parameters. The public key derived from this group information and the private key of the server. It signs this group information with its private key to verify, and the client then can verify with the public key of the server, oh yeah, the server actually signed that, also selects, based on the group, its own private key, sends a public key, and through Diffie-Hellman, math, and magic, we have a common pre-master secret, and we both can do this change cipher spec, which is just a fancy name to say, let's switch to encrypted, because we both have the same secrets. If they don't have the same secrets, then at the end, some hash sum, so this MAC will just fail, because they don't speak the same. And you may wonder why we have this random here, and on that side, That's the protection against replay attacks. So every site, for every connection, picks a random value, and they also affect the final MAC. And if I would ever just record traffic and try to replay that, I would get a different random back from the server, and I could never ever get the right hash sum at the end, the right MAC, and that protects against replay attacks. And yep. So we have the Diffie-Hellman key exchange, which is something called perfect forward secrecy. That means we throw away this shared secret at the end of every connection and make a new one. So that's the E in the elliptic curve ephemeral Diffie-Hellman. Ephemeral means one time, throw away, forget it, short time memory, yeah. Although in TLS 102 it's not yet fully perfect forward secrecy, it's fixed in TLS 103, but it would be too long to explain why. It's still not very secure. And OpenSSL, if you use the client tools, looks a bit like that. And so with OpenSSL client, that's now going to the next step of diagnosing connection. It gives you even more low-level information, lots of text. It looks a bit confusing at the moment, but these two blocks here, the blue one and the green one, information about the certificates. And the last block is just an indented block. It gives you the protocol, the cipher suits, and that master secret is the actual encryption secret derived from the pre-master secret and verification information. Yeah. I also promised you a while back ago, instead of like raw TCP dump, to show you a better tool to see what's happening on the wire. And that's the tool called Wireshark. So that's also a session. I wrote a rule, made a connection, and now I have made a connection to the client, filter out all the stuff I'm not interested in, only want SSL. You see, I have a client hello, TLS 1.2 eventually, the framing is TLS 1.1. I have a cipher suit, also send the host name, that's important for virtual hosting. And the server sends back some information. Oh, it agreed on TLS 1.2. It agreed on the cipher suit I selected. It's flickering. Well, hope you can still read it. I also get a bunch of certificates. That's the next step in my talk. One for the end server, one intermediate certificate with different values. You can actually explore what's going on internally. It's very, very useful to read this kind of information. I have the key exchange with like the Diffie-Hellman parameters. I have the public key and the signature, and that's the signature value. Send that to the client. The client responds also with Diffie-Hellman key parameters, the public key of the client. And finally, we switch to TLS, and the rest is then now encrypted. From now on, we have the full handshake. We are encrypted. And this is a very useful tool to log into a server. And since you don't have this kind of tooling usually on a server, you can also use TCP dump to dump your traffic, download the file to your own machine, and use that tool to see what's going on. Okay. Last part is the certificates. I think one of the most mysterious parts, and in a whole different story, because now we are leaving the network layer and going to very old standards called X509 certificates. Certificates are like proof of some crypto information plus a lot of metadata and settings for verification of your peer. The bank or the website has a certificate that is signed by another certificate and usually then signed by somebody that's like a trusted person or trusted entity. That's called a root CA. So they come in different kinds and shapes, but they're basically all the same. So if you have heard of SSLError or DER, that's just the binary A's in one. The PEM files you often see, they're just base64 encoded certificates with some header and footer like begin cert, end cert, begin private key, end private key. And they always come like in a pair. You have a private key, only you know, hopefully. and the public key that's part of the certificate, and lots of other information. And to view them, you can use your browser, or again, the OpenSSL command line tool. That's now the subcommand X509. Before that, I used the subcommand S-client. That gives you out a long output, which looks also intimidating at first glance, but it's not that complicated. So let's start. We have a version 3 certificate. That's pretty much all you will see these days. Version 2 I've never seen in real life, and version 1 is very rarely anymore. They have a serial number that's counted up, or these days randomly selected for security reasons. It's always issued by somebody, so that's the party that signed the certificate. It's only valid for a couple of months. That one would be already invalid. That's from Czech Republic. You have a name, so that's the certificate is valid for your server, and they have some public key information. That's the public key for your cert. A couple of extensions. This certificate is valid for RSA key exchange and elliptic curve key exchange, valid for web servers and web clients. It's not a CA, and some other information that is a bit of a scope for this talk. It also is valid for a certificate host name. That's this extension here. And finally, signed by somebody. And in real life, you see mostly 3 kind of certificates. The first one are the root CAs, or called trust anchors. They're installed in your operating system or installed in your browser and shipped with your browser. These show you, these basically are the trusted entities that will sign a chain of certificates. Then you have the intermediate CAs that will sign the end certificate. And you have the end entity or server certificates that will then be used in your browser. So why don't we use the root CA directly to sign? Because the root CAs are very precious. They're usually taken offline. The keys are stored in a vault. Nobody can access them. And we use like intermediate CAs for security reasons. And they're usually also stored in special hardware. The root CAs had some flags, so it's CA true. The intermediate CAs has some flags look a bit different, and the end entity too. So the only difference between a CA cert and an entity cert is this basic constraint CA equals true, and which kind of key usage is allowed. Other than that, they look all the same. And yeah. If you use the S-client, you see this chain. So the server sends back its end entity cert, and the intermediate cert doesn't send back the root cert because that's already installed in your operating system. And if you wonder sometimes why you have this fancy green bar called extended validation certificates, they just do some additional steps to verify you through kind of notary service. The certificate itself, technology-wise, just has an additional field in the extensions. And very important, please keep your private keys secure. Don't throw them in your bin or make them public. So, final step is, 5 minutes, perfect. Cert validation issues. What can go wrong if something goes wrong with certificate validation? Just to give you some examples, if you use Python 3.6 or earlier, you don't get that many information. So I now use S-client from OpenSSL again, and a tool, a website called Bad SSL that just has bad certificates on purpose to do verification and just examples. For example, error code 10 certificate has expired. Yep, so it's no longer valid. The field that says how long it's valid is in the past. So if you get that error, it means you have to renew your certificate somehow. Sometimes, very rarely, the error message is not yet valid. That sometimes means that your clocks on your computer are out of sync. It's also sometimes, but it only happens if you create your own certificates, you have some very strange handshake errors. I had that issue once, took me half a day to figure out my own mistake, is when your key usage is wrong. But in practice, no, you won't see that in real life. There are also issues when this validation of the chain fails. Something is the error message self-signed certificate. That also happens if you do local testing, do something wrong with your own test certs. More common is the error message unable to verify the first certificate. That means that your server only sends the end entity certificate and not the intermediate certificate. So it doesn't send the whole chain, only like the beginning of the chain. All are unable to get local issuer certificate. It's just another way to spell out it doesn't know your root CA. It occurs if you have your own CA and didn't install it. Or the error message self-signed certificate in the chain means the same, except the server also sends the root CA. And if you use Python 3.7, if you update, then you will actually get this error messages also in the exceptions. That one of the improvements are added to 3.7. It will help you a bit. So quick look, root CAs, so these trust anchors, depending on your operating system and your Python version, they can come from different sources. Linux users have them usually in a specific file that depends on the distribution. Windows has them in different places, and macOS also. This is a bit painful, so there are different paths, different locations, and we currently work on improving that. There's a helper function in the S module. You can get like the pre-configured, pre-compiled paths, and you can look at the things actually there. You can install what request stuff, the certify package, which just contains a pre-compiled list of root CAs and just injects them into Python. But you have to keep them up to date, or you run into issues I had like with New Relic, where they shipped a very, very ancient version of the root CAs, including root CAs that are no longer valid. And the final step that may sometimes fail in rather funny ways is we have to send the host name during the Ssl handshake. So that's you make a context wrap socket, you have to pass in the socket, and then server host name. And that sends the host name to the other side, and also verifies that the host name other than the subject, or these days in this extension, verify and match. It's very hard to implement correctly, so I fixed a couple of bugs in OpenSSL, now moved to a new API. And this is also important if you use virtual hosting, because you have to send the server host name to get connection to the right host. Because when you connect connection to a server, you only connect to a TCP port combination, and then tell the server, I want to select that host name. If you do that the wrong way, then your browser may just show the right page, but your Python program may go to a wrong host or get very strange error messages. I'll skip that because I'm only running out of time. Yeah, that's the remark for HTTP2. So you have to do the right combination of server host name and HTTP host. If you don't do that, again, it fails. So it's a list of tools I showed you. Recipes to use like check connections, go to the S client, use curl, TCP dump, and using Python 3. Here and a couple of other tools and links. I'll put that up when I do the slides. And if you want to learn more, I highly recommend these two books, especially the one on the right. It's a bit hard to read. You can still read the title, Bulletproof SSL and TLS, by Ivan Rischek. It's the most up-to-date and best book to explain the whole list of best configuration, how the handshake works, how certificates works, attacks over the last 5 or 10 years, what kind of problems and bugs were found in the protocol. You don't need to know much about crypto to understand that. It explains also the crypto parts very good. Yeah. And Lucy, let's encrypt, or software I'm working on, and questions.
Hallo, zuerst vielen Dank für den Bericht und ich habe zwei Fragen. So first, you have mentioned that Russian PyCon's website is not secure, yeah? So I wonder if you have tried just for fun to catch some traffic. I'm just asking, so you cannot answer if you want. And the second one, you have not mentioned about the man-in-the-middle attack when you were talking about TLS with different element, for example. So my question is it still possible with this crypt algorithm? So thank you.
So man-in-the-middle attacks. So man-in-the-middle attacks means that you, just for the others, that you have somebody who intercepts the traffic and can modify the traffic. If you use the modern algorithms and the modern ways how you use certificates and have the correct trusted CA in your browser, then to our current best knowledge, man-in-the-middle attacks are currently not feasible and possible. There are attacks like internet worms that try to inject wrong CAs into your computer, or like they have like multiple incidents over the past 5 years where like drivers from, like, I think Lenovo had a root CA that was publicly available, including the private keys. So if you have wrong or dangerous root CAs in your computer, or have misconfigured your Python context, so don't enable hostname verification and don't enable certificate verification, then you're still subject to man-in-the-middle attacks. But if you use what you have by default in your Chrome or your Firefox browser, or good root CAs, including secure settings with a great default context in CPython, then to our current best knowledge, the crypto world thinks we're secure. But we never know what like the big three-letter acronyms agencies can do. But yeah, I think you can be pretty secure.
Hi, thanks for the talk. I have maybe a naive question. So let's say I open a page in a web browser and it works. Then I use Python to fetch it, and it gives me handshake failure. So first, like, I can debug it. I can figure out that maybe some cipher is removed from Open SSL. I don't know, but maybe like, is there a way to make Python work the same as browser? So like, if you can open it in browser, you can open it in Python.
Yes and no. So one thing you could do, if it's just a cipher suite problem, you can use like Wireshark or TCP Dump to see which kind of cipher suites are agreed between your browser and the website, and then try to set the same settings as the browser would set in your Python program. That works good. There are other issues. I didn't go into details regarding intermediate certificates. So browsers can do something called authority information access chasing, AA chasing. So the end entity certificate has a field that explains where you can download the next certificate in the chain. Browsers can download this certificate and cache them locally in their secure store and then build the chain more intelligently. Python doesn't have the capabilities to like fetch this missing certificates from the chain. So for that, you actually need to figure out or fix the configuration. These days, at least the website I know, all configured to deliver all the correct chaining information, but there's still places where that goes wrong. Or I had issues with some website related to request read the docs a while ago, where they had not only the primary chain, but also an alternative chain. You can do like multiple chainings in the communication that's even more complex. And they had a chain with a certificate with an old kind of signing algorithm that also failed. But again, to go back to your question before I go too far, so I would start by using Wireshark and TCP Dump to see which kind of protocols, which kind of cipher suites and elliptic curve parameters the other side has. And it's failing on like with the cipher suites, then you know you have to change the cipher suites. If it's writing certificates, then it gets a bit nasty if the other side is slightly misconfigured. You can bit workaround and download this intermediate CA and install it in the trust store. I think we can take it offline and talk about that later on, drinking a beer or so. Okay, we had one question there, and we had one question over there. But you already got the microphone. You're next up.
Thank you for talks. Firstly, I want to say about previous question. Google Chrome has a great tool. It's opened by about.net internals. They shown any network activity very detailed, and maybe you can find some helpful info here. And my question, what happens if one of private key of root CA goes to public?
Pardon me, I didn't get the last words.
For example, in my operation system installed many root certificates. What happens if private key of any of that certificate go to public, and anybody could use it to, for example, make a MITM attack?
So it depends on which level. So if the end entity certificates get like compromised, then there's two protocols, Certificate Revocation List and OCSP. It's online certificate status protocol that can be used, but Chrome doesn't use these protocols because they had also downside. They're slow and big lists. So Chrome internally has an internal list of certificates that get blocked. They just record like which CA signed the certificate and the serial number, and they have like a large list they can block. They do it for high-profile certificates. They also do that internally for intermediate CA certs. They have also, both Firefox and Chrome have special algorithms internally where record bad CAs and intermediate CAs, sub-CAs. There's no facility in Python itself to do that because it's not that easy to hook into OpenSSL at a certain point. That's on our list. So browsers can do that because they give out updates very often. So daily you have to download a new version of Firefox to get like that blocked. If a root CA is compromised, then you also have to get a new update where the root CA is either removed from the trust store or flagged as bad and untrusted. Or if that hit in the news, you can as a user also disable a certificate, a root CA in your browser. But for root CAs, there's no protocol because root CAs are ultimately fully trusted. So there's no query protocol because then you will need another CA to just sign this information that root CA is okay or broken, and you have like a chicken egg problem. So install updates always. That's the only way, and hope that browsers react fast enough to compromise.
Okay, thank you.
Yeah.
But it's...
Maybe I didn't get your question right, but again, let's do the other question, and we can talk about over lunch.
Yes, thank you.
Yeah. I'll stay here until Monday evening, so enough time to grab me if you have further questions. Wait, one question in the middle?
Yeah, probably last one.
Yep.
Hi, thanks for the talk. I've heard that having service certificates signed with weaker or older algorithms is a bad thing, but somehow for CAs, that's okay. Could you please explain?
Yes, so the reason why a root CA that's okay is because root CAs are never verified. So you have the public key in your browser installed, and if you verify the whole chain, so there's a rather complex algorithm that builds this chain and then verifies the signatures. The signature of the root CA is never verified unless you set a special flag which is never used, just for debugging purposes. So you trust the public key of the root CA. You don't trust the signature of this of the root CA. So it really doesn't matter what's in the root CA. It only matters that the root CA's public key is fully trusted. And you don't need to verify that the root CA has signed itself. So root CAs actually are self-signed certificates where the root CA uses its own private key to sign itself, but you don't need to verify that. You can just assume it's okay. That's why it looks a bit silly.
That's way more clear. But why is it not okay for service certificates?
Because for the services, when you build this chain and then verify the signatures, if there's a weak algorithm, then it's possible that an attacker can spend enough CPU time to forge a certificate. So it could just create a new certificate with its own private key and then invest money and CPU time to create a so-called forged signature. Because for weak signatures, if you like SHA-1, that's actually doable these days. If you spend enough time on AWS, you can create a SHA-1 signature that has the same value as a value of a known entity. That's a trick. And for weak one, it's just fast enough. You don't have to spend that much money. And for the newer hashing algorithm, it would take like several thousand years or tens of thousands of years to do that. And it's just not feasible.
Great. Thank you so much.
You're welcome.
Chris, and you should select the best question.
Oh no, they're also good. I think the one on the back there.
The question about?
Yes.
What the question was about?
Sorry, I'm a bit stressed out and forgot the question. But I remember the person that's sitting like in the middle of the right row
In
on
the
my
middle
side.
of the right.
He's already gone?
Кто задавал вопросы? Поднимите руку, пожалуйста.
At the back, yeah.
Михаил.
Ah,
Okay, thank you, Chris.
you're welcome. Thank you. And just talk to me. Don't be shy.